Okay, so yes, so up to with the last talk, we hopefully learned first of all what is class S, and one thing that we should know a little bit by now is how to play with Schaeber-Witten theory and how to write down curves, and from that we can calculate the tau IR. Another thing was this, yes, what is class S, and we learned how to decompose the different curves and how to define this class of theories by having the 2,0 theory on referent surfaces. So most of these other things we didn't talk about. Maybe Abhijit, at some point, he explained these things here, so maybe people know. But anyway, the motivation for this work is that we have all of these different beautiful ways to obtain exact results for theories with n equal to 2 supersymmetry. And the idea was how to try to do something similar for, at the beginning you want to ask the question what you can do for any n equal to 1 theory. And then very soon you will decide that maybe there are certain classes of theories that have better properties. So, okay, when you ask yourself what I know already how to compute, well, this is the first thing that comes to my mind, which from the beginning when you learn how to compute the index is an n equal to 1 thing, so that immediately goes through and you can do it. But, so maybe something that, for example, I didn't learn when I was a graduate student and I learned it only afterwards, is that immediately after the original Seiberg and Witten paper, there were papers by Intelligator and Seiberg that studied generalizations to n equal to 1 theories. So they wrote down curves that compute the tau IR. And there was even, so this Witten approach to obtaining the curves from M theory that we learned how to do in the last two previous lectures, he generalized it to cases where there is only n equal to 1 supersymmetry. And in fact, when he was writing this paper, at the beginning I thought he will solve everything. So he has a crazy statement in the paper like, are brains magical, in the sense that brains know everything? But I think in the end he was not able to show everything. So at the end of the paper, I think he looks more disappointed. But maybe he wanted to really solve everything at the beginning, yeah, with one paper, so it didn't work out, but okay. And what is very important for n equal to 1 theories, we do not have the equivalent of Nekrasov partition function, so we don't know how to write down instantons for n equal to 1 theories. And also we don't have Pestun, but okay, for this talk it's not gonna play a role, but to be honest, when I started thinking about this problem, I was started thinking, and you will see how through AGT basically everything comes in the play. So, good. So now we want to decide how to choose. Yes?
In the original Seiberg-Witten paper, they talk about n equals 1 deformation, right?
Yes.
In the context of
Yes. So this is the theory that Witten wanted to solve.
How do they go to n equals 1?
So you make a mass deformation to the phi.
To the phi.
Yes.
But then you lose the Coulomb branch, no?
Very good. So you don't want to do that.
Okay.
Yes. So this is a hard theory to play with, as we will, yeah. Very good. So, okay, how can we start thinking about getting a good theory? So one question, first of all, if you know the NSVG function, immediately you ask, can I even have a conformal theory? But this question was answered long ago. And in fact, you can ask that I find the solution to the NSVG together with the coupling constant beta function for the superpotential that you may have, and they may have common solutions, and then you can find like these fixed points. So this is what these people did. And then we learned ADA-CFT, and there you have many ways to get conformal theories. And for what I want to do, the orbifolds will be the best way to go. Of course, for example, you can try to ask maybe the question, this beta deformed, how maybe you could do similar. So there are a few things that are ADA-CFT inspired that you can immediately start asking different questions from them. And then, well, this is the modern way to do things. So the same way Gaiotto told us to take the 2,0 and put it on a Riemann surface. Now what people are doing, they take the 6D 1,0. There is supposed to be a classification if you believe in F theory, that F theory knows everything. you put them on Riemann surfaces, and you are supposed to be getting a huge class of n equal to 1 theories in 4 dimensions. And there is a subclass of that Baffa would call Sk, but the original thing was S gamma, and Sk was, the original thing was written in this paper in 2015 by Shlomo and Gayotto. So this is a class, I will introduce this class very slowly, but very quickly what happens is, of course, this is a class of theory that you obtain by orbifolds, and it comes out to be conformal immediately. And what was amazing about this paper is that you classify the theories by having a Riemann surface and punctures on it, and you can label the theory by telling me what is the Riemann surface and which punctures you have. And this is, like the same way we had in n equal to 2 theories, this is beginning to discover 4D to D relations. And in this paper, they used the index as their main object. And they were able to do the same thing that was possible for n equal to 2 theories. They were able to rewrite the index as some type of 2D topological field theory correlator. And basically, okay, when I saw this, then, I mean, it was clear that what was the question I asked. Is there any way to get the other 2D 4D relation? So to have an AGT K, so a way to get 4D partition functions from some 2D CFT calculation. So that's the question that I asked. And if you can find a way to guess this, you win, you will be able to write this thing down, and in the end you will even get not only Nekrasov, but also Peston. So, okay, so this is the plan of the talk. So first we will introduce these theories a little bit more carefully. Then I will tell you how to derive spectral curves. I will give you one way. Of course, there are more ways with which you can do it. Then I will tell you the moment you have the curve, how you can start to try to guess what is the 2D CFT, precisely the same way we talked about last time. So by looking at the coefficients of the curve, I will start guessing what is the symmetry algebra and what are the representations in which our vertex operators should live. And the moment I have symmetry algebra and representations, I will basically just be able to immediately write down conformal blocks. And if such a thing exists, this thing gives a guess for what should be the instanton partition function. So it's just a formula, you write it down. You are not 100% sure if this should really mean something or not, but you write it down. Then you need another independent calculation to try to see if this thing that you wrote down makes any sense. And this will be the next step that we will try to take. So I will discuss a brain setup that I will put on an orbifold precisely the same way you should do in order to get this class. And I will try to argue that if you do this, you will be able to calculate the partition function on these dp minus 4 brains, and you will get precisely the same answer as this.
But the theories that you construct from the last approach,
This is the last approach.
It's a special class of it.
This is true, but you see also, for example, for general class SK theories, nobody, okay, and now I am being very strict because of course I have papers on this topic, but nobody can write down the instanton partition function for Tn. So what human beings are doing is that they are writing basically for the equivalent of the theories that I will write things down. So I am as good as n equal to 2 if you accept all of this. Having said that, I am working on how to, I mean, okay, we can, yeah. So it's not out, but okay. That's another discussion. So let's introduce the class SK. First of all, this is the beginning. So the same way to get n equal to 2 theories, you just take NM5 brains, you put them on some compact manifold and some Riemann surface. By the way, when the compact manifold is S3 cross S1, you have the index for the 2D relation. When this thing is the 4 sphere, you have the AGT relation. So appropriate twisted compactification on this gives you the gauge theory on this compact manifold. Appropriate twisted compactification on this gadget gives you the 2D theory that you are looking for. So instead of starting with the 2,0, what you do, the 2,0 is the theory that lives on N5 branes, that is the A of that. There is AD, so the A lives on N5 branes. So you do a transverse orbifold. And then you get N1,0 six-dimensional theory. And this is the one that you are supposed to put on Riemann surfaces in order to get the classes K. So that's the definition. Now,
What is the asymmetry of this?
good.
1,2.
Let's continue because they will all come. So here I start putting everything. So a little bit, so more friendly to the user is the type 2A description. And here, if you delete this line, the last line is precisely what we were doing before, and we had n equal to 2 theories. So here, this was the x4 and the x5 is what I made to this V complex coordinate. So this is the U1 R symmetry of the n equal to 2 theories. This is the U2 R symmetry of the n equal to 2 theories. And the moment I allow for this orbifold to go there, I break the SU2 down to its U1. And this is very visible in this picture. Now, I was also drawing last time this type of Hanani-Witten diagrams, which were good if I wanted to describe the Coulomb branch of n equal to 2 theories. So if you plot 4, 5, and 6, you see here what you have to do is orbifolding means, let's for example do Z2, which is the easiest. It's like putting a mirror here. So if you had here a D4 brane, you need to draw its mirror image downstairs, and you need to do this for everybody. And if you want also, you can do precisely your supersymmetry counting and precisely find which supersymmetry charges survive the orbifold projection. So you can really write down everything. Now, another description that is very important, and I will use it when I will want to do my instanton calculations, is the type 2B1, which is obtained from the type 2A by doing a T-duality along this. So I compactify S6 and I do a T-duality. And this is what I get. So again, this part is precisely what we had the previous time, the previous lectures. And this is what is new. I just copied. There is nothing happens here. So when we look at this, this is very useful because first of all, we recognize that it's an n equal to 1 orbifold daughter of n equal to 4 super Young-Mills. So it is one of these theories that the all the ADCFT people were studying. And not only that, you can really go through the literature and find already results about this theory. And in fact, even people, because instanton is the thing I care about, people had started looking at instantons back then. They never wrote a complete answer because I was, when I did the first calculation from the blocks, I thought that maybe I can, find one paper and, check. They never brought the whatever thing they wrote down to a form that one can really check. But people were actually doing this. So that's not a crazy thing at all to try to do this. Good. Now, completely from the gauge theory point of view. So first of all, for the n equal to 2 theories, first of all, these are the theories that, let's say, the core theories from which you study and you learn basically everything you want for class S. So I take a linear quiver like this. And now I wrote everything in terms of n equal to 1 language. So I wrote my superfields in these different colors. And Q and Q tilde are the ones that make the hypermultiplet. And the phi is the adjoint guy. And the moment you do the orbifold, and in one slide I will show you precisely how to do the orbifold, you get this type of quiver. So you break you have a non-chiral quiver for n equal to 2 theories, and then you get a chiral quiver. And not only that, the moment you write down this, it's a little bit of an intricate quiver, but still, because of its symmetry, it has a lot of U1 symmetries that when you write down all the superpotential, you can start checking that they are all there. And in fact, in the original paper of Gayotto and Razamat, yes, so this is what it means, that it is on a cylinder. This is why I have this line. In the original paper, they even checked that these U1s that I have on this table, I mean, you don't really need to look carefully because I'm not gonna, they are more important when you study the Higgs branch. For the Coulomb branch, they are not so important. But they are all anomaly free. So it's really good. There is a lot of symmetry going on. Good?
Sorry, from
Yes.
the previous point of view, you had a U1 times U2 of the n
Yes,
equals to
very
2,
good.
which
So
was
there is
broken
a
into 1
linear,
times U1.
there is a linear combination of this one with this one that you will allow you to define one U1 that will be linear combinations of the R U1 and the little r U1.
So what are the other two?
The other two are things that basically label, when you write twisted operators, which I'm not gonna do, they label all of this type of operators. We can talk more about this afterwards because I'm really not going to use it. But if you want to study the Higgs branch, actually this is becoming important because this is how you classify your stuff. Okay, so now, again, we did the Douglas and Moore projection last time for how to go from n equal to 4 to n equal to 2. So here you do precisely the same thing. It's just that now the orbifold lives in these directions instead of these. So that's the only thing you change. You change precisely on which x4, x5, x6, x7, and x8 and x9 combinations you act. And this is what you get, and you plug in and you get your Lagrangian like this. So this is a very easy thing to do.
By the way, if you had started with n equals to 2 theory, which was circular,
Yes.
then with this you would get something which is like a torus.
Precisely, very good.
That's
So-
nice.
So what you can do, and I take it for granted that you can do it, that's why I didn't even say, I should have said it maybe. So the same way you make this identification, you can make this identification, and basically when you do the type 2b orbifolds, these are the theories you get, the toroidal toroidal quiver. So, and in order to go to the Hanani-Witten picture, you need to engage one node to be able to open it up, basically. That's what is happening. Very good. So we have all of this, and this is just a very little comment. I don't want to insist. So in the very first time, I said already what is the difference between the Coulomb branch and the Higgs branch for theories with n equal to 2 supersymmetry. So there is this U1R symmetry and the SU2R symmetry, and the operators here are charged under this one, and the operators of the Higgs branch are charged under the SU2R symmetry. So this thing, precisely because you have, we have at least two U1s, I can always play this game and define my Coulomb branch to be made out of the operators that are charged under this one, and the Higgs branch, the ones that are charged under R and not under this little r. And this again, it can be achieved if you set all the q's to 0 and give value and give vebs only to the phi's. Of course, now the phi's, they are bifundamental, so they are not going to lie in a diagonal matrix immediately, but you can always do a similarity transformation and bring things in the diagonal. And because you are doing this, and your phi's are bifundamental now, you cannot have like what we had before, trace phi to the L type of operators. You cannot do that. You have to always, if you want to make a gauge invariant combination, multiply all of the different phi's. So when I write phi 1 to phi k, I mean, sorry. It got, no. You need to multiply phi, all of them and go around. And only these objects now will be gauge invariant. So that's
actually a bifundamental.
Yes. So that's important. But that's what it is.
But the number of things you have is...
So good, you need to count your parameters. Precisely, yes. So it's good.
Oh.
So I will use the same counting.
Sorry. Can you go back to the picture?
Yes.
So imagine this is also compact file.
Yes.
Elliptic system.
Yes.
Now, I would have thought that cycle is symmetric with respect. I mean, symmetric. These two cycles are symmetric.
This one.
Yeah.
Good.
Is
So,
there some sort of a triad going
good.
on?
In 4 dimensions, I think you have to be very careful with these statements, but
Because this brown arrow,
yes,
the red
yes,
arrow,
yes,
I can
yes,
go
yes,
around
yes.
and construct cycle.
Okay, this good. Yes, but not quite. Because the moment you choose what is your U1R and your big R, you break the symmetry.
Yeah, I agree, but a priori there
Yes.
is some automorphism of this.
Yes.
Some Z3 automorphism. Which one you call phi? You can
Yes.
either call the blue line blue circle.
Very good. Yes, yes,
Or the
yes,
red or
yes,
the green
yes,
one.
yes, yes,
Okay.
yes. Actually, yeah, maybe one can try to use this to constrain the index or something. Very good. Good. So, but yes, this is the important thing to remember, that we are allowed for this class of theories to separate these two branches. And why this becomes extremely important? It becomes extremely important when you want to study curves.
So
Yes.
the Higgs branch, can you tell me the Higgs operators?
I mean, I cannot tell you everything because it would take forever, but they are again QQ tilde type of guys, but you have to be careful with how you color contract.
Yeah, so on the previous line it's nice to see. It's probably easier
Here.
to see, right? Yeah.
Yes, so you can start making operators like this. Tac, tac. That's a good operator.
No, you want to make gauge invariant.
No, this is gauge invariant. So here,
Sorry,
this line,
So let me just consider the torus.
Yes.
Let me compact. Let me identify this also.
very good, very
And
good.
then
So if you identify, you can have, okay, for example, okay, let's be stupid. This is a gauge invariant operator. It's some type of baryon, right? That's already one of
is
your.
it that or you want QQ tilde like zigzag, zigzag, zigzag?
So,
all the way up?
so good, good, good. QQ tilde is meson type of operators. Only Q and only Q tilde are baryon type of operators, and they will obey the very similar relations to the one we know from n equal to 2. So B tilde will be equal to some meson to some power, some determinant of mesons. Exactly. But a little bit you have to be careful with how you do your color contractions. Now, I want to study curves, because this is for sure what we learned that works. And again, what the curves do, now we don't have n equal to 2 supersymmetry, so we should not think that we will get the full prepotential, but we should be able to compute the effective coupling constant in the IR. That's holomorphic and we can get it. Now, okay, maybe let's first say, when you do n equal to 2 theories and you want to put them in M theory, what happens is that you have, of course, the 4 dimensions in which your gauge theory lives. And then you have this. So this is where you see your SU2R symmetry. And this is the cotangent bundle on your curve. By the way, remember that this thingy is where this meromorphic differential lives. And to make the cotangent bundle, I add to it this coordinate V. So I have a line bundle that is labeled by V. Now, in order to do n equal to 1 theories, I don't have this nice thing anymore that 3 things are here. Only 1 is here, and I have Calabi-Yau threefolds. So I have these 2 line bundles. So I will have this and another one, let's call it W. And they will be, this is G. G, comma, N. Now, first of all, if you do this, people have done it, and they wrote down curves, and people studied very seriously all of this stuff. And what you get is something, first of all, that is very scary. So you get an algebraic system of equations that it's like good luck solving. Of course, they have tried to play, and they can do tiny little bit things, But in general, this is a mathematical problem that is called the generalized Hessian system and is not known how to solve. So mathematicians don't know how to do it. So yeah, this is very hard. And this is why choosing this class SK is very good, or in general this class gamma, because what it does is that it trivializes this W coordinate, so you don't need to consider it anymore, because you go to the Coulomb branch and you have again a structure that is like this. And this you achieve just by going to the Coulomb branch. So this is very crucial.
So what does it mean? N equals 1 spectral curve is an overdetermined algebraic system.
Say again?
N equals 1 spectral curve is an overdetermined algebraic system.
Yes, so you don't get, okay, let's maybe,
So the spectral curve you're taking it taking as an input from
let me go maybe here. So what you need to do if you want to have everything is you need to define one complex coordinate like what I did with x4 and 5. Another, let's say, complex coordinate, this is what I was calling W. By the way, what I am telling you is also what precisely Witten did in this paper from M theory. And then you define this S, which was this x6 plus I x M theory. And your algebraic curve now is something that lives in this 6-dimensional space. And one equation is not enough to, because if you go to the Higgs branch, things will also happen with W. So usually you get a system of equations. And usually it's overdetermined, so it's really hard to open it up and to understand it. That's what it means. Good, so that's why this is very important. Now, good, so this, by now we are experts, right? We explained it very well, how to get curves from this nice picture. So I am not going to repeat it, we just make sure that the curve goes to 0 when we write it as a polynomial in T and in V. So now to get the class SK curves, you do exactly the same. You go to the Coulomb branch so that nothing happens in these extra coordinates. All the physics happens here on this 2-dimensional plane. And you demand that not only for the original branes, but also for the mirror images, the curve has to be 0. And you immediately do the same, and this is what you get. Now, one thing that one should, for example, what I did here is the equivalent, so this was for SU2 with 4 flavors. This is the equivalent when I will have SU2 color factors. So of course, first of all, you get a higher polynomial in V, so you get a 2K, because these are how many images you get. But another thing to be careful, before we had only one U. Now we have 2, and in fact it makes sense by counting. We have one U when I multiply all of the phi's, and one more when I square them. So it matches also with what we know from gauge theory thinking. So we get these 2 unknown parameters. Good. And this is a condition how you impose the... And by the way, something that, because now I will start going to the Gaiotto form, exactly because I impose this condition of the orbifold, I am not allowed to shift V anymore. So this shift of Gaiotto is gone. We cannot use it anymore. Yes.
So the way curve knows that this is n equals 1 is by that orbifold.
Exactly. With this
By
precise...
that, this could still mean some n equals to 2 theory.
If you could write your parameters more generally, it could be. The very important difference is the fact that I put this to the specific places and the fact that I now have 2 U's. Whereas before I had 1, and the second parameter here was just the sum of the masses. Now this is going to be something more complicated. And it's going to depend on the coupling. Now, So first we learn how to do curves, and the second step that we learn how to do, because this was what we needed to discover this class S, was to go to the Gayotto form. So you can do precisely the same thing. You can start with this type of curve that just by looking, what is it? Is a kn minus 1 genus surface. And you want to write it in such a way, precisely the same we did before, to view it as a sphere with punctures. That's what you want to do. And you can do it. It's precisely like what we did before, is a rewriting. I do precisely the identical steps that we did. The only thing that I'm not allowed to do again is this Gayotto shift. And this has consequences, and you can see them with your bare eyes here. So before, for n equal to 2 theories, because of the Gayotto shift, we had a square here. So now this is a simple pole. And this is going to remain like this always. So when I have a simple puncture, it's going to come with a simple pole. Second very important thing, here, before we just had this L. Now it always is multiplied with a K. So whenever you have a full puncture, it always comes with this higher power. And, okay, first of all, one very simple thing like before, you should first decompose your 4-punctured sphere to see what you get. This is what happens. You get a curve that looks like this, which is immediately interpreted as a 3-punctured sphere, which is just or befolded hypermultiplets. So this is immediately like this. And so you can either compute it by doing the weak coupling limit, or you can compute it from scratch and check that you get the same thing. And then you can also play the same thing that we played when you do all of the different decompositions. So if you remember, we had the q to the 0, the normal weak coupling. We had also this q to infinity, which corresponds to exchanging the NS5 branes. And this is really basically giving the same thing as here, just by changing the masses. So basically the M2, M1, M2 goes to M3, M4, like what we had in the previous time. But of course, clearly here you get something more advanced. And this is the equivalent of the Tn. And in fact, you have to do things carefully. And here you even get a new type of puncture. But let's not go there now, because anyway, even for class S, this is hard. So this is where we stand.
For SU3, it was...
The E6.
Yeah, so here also it's E6, right?
No. No, there is really a new type of puncture here that is not the same as these two, and it has another type of symmetry.
And for SU2, all punctures are of the same type?
No, because SU2 now is more similar to SU4. I mean, also it's visible from this stupid picture. So you would have to U once to get something more similar to SU2. Good. So we have this. And now I want to go to what I was trying to say last time. But let's first, okay, so this is what I was explaining last time. But let me even before go to, this was how to alternatively derive a GT. But let's first recall a GT. First of all, what we did in this type of decomposition picture, we started discovering that there is some type of S-duality in the gauge theory side, in the UV, and this corresponds to crossing symmetry in 2 dimensions. So that's clear. Another thing that is very clear is that the masses, because of this precise way how we decompose our curve, they should be mapped to some external momentum of the vertex operator. That should also be very clear. And also something else that should be very clear, the coupling constant, because this is how we did this as duality business, it should be mapped to cross ratios, to how the moduli of your curves. So that's very good. Another thing that should be almost clear, if you remember what I was writing last time, was the fact that the Coulomb moduli should correspond to the internal momenta, because when I decomposed my curve, I got that one of the masses of the three punctured sphere was proportional to A. So when I was engaging, A was becoming, so this is precisely the one that runs inside the internal. So all the basic dictionary we have of the parameters, and the most advanced thing is that, and this is precisely how they got it. So they started looking at the instanton partition functions, and they started doing this type of S-duality transformations to them. And they realized that they have seen this equation before in the yellow book. This is how the conformal blocks transform. So very soon, and by writing things down, you recognize that the instanton partition function should correspond to, and basically because of S-duality. So this is the way you see this. And then, of course, you have to write all these ugly formulas and start checking order by order. Now, one thing, and this is where AGT were super lucky, is that what is left over is the perturbative part here. And in fact, to be more precise, the tree level, you put it here with the instantons. It's a normalization that you need to put. So here what I really have is the determinant of Pestun, the one loop calculation. This has to somehow be matched to these 3-point functions. And they were very lucky because they had the explicit expression of Pestun. And basically, Liouville was the only theory for which, in some sense, the 3-point function is known.
Sorry, but you said it's also the unique solution to the bootstrap equation.
Yes.
Not just that it was known, but you're saying that has to be the case.
Yes. And they looked at it, and it was the same. So basically, you just write things down and you just look. And it's maybe a small exercise on special functions to realize what is going on. Because at the beginning, actually, Pestun didn't use this epsilon wave function. He was using some other, the Barnes. But if you make your homework, you can realize that this epsilon is coming out from the Barnes. So you are happy. So then the moment you see these things, the only thing that you need to identify for this thing to work is that the omega background with which Nekrasov was regularizing the IR correspond to coupling constant of Liouville in this way. And the moment you know this, you are done. That's AGT. And you can claim that it's a mathematical relation in the sense that all of these special functions work out, but this is what it is. And it all comes from S-duality, I want to say. So now, what we said before, like at the end of last lecture, was let's try to take a more stupid way to try to rediscover AGT. And let's repeat it because this will be the way I did things here. So first, you look at the poles, and you see this power, and it is suggestive. And you do the following computation. You compute, again, you can do free fields, weak contractions. You compute, so because this looks like the word identity, right? So you compute this ratio. And the moment you compute it, you have, P1, P2, P3. You can immediately make the parameter match, and then these are completely equal. These are two functions that are not, they are not trivial functions, and they are completely equal. And you again can do, again with free fields is super easy, by inserting here higher currents, this computation, and you on the nose get all the coefficients from the curves. And for free trinions, this is a super easy homework to do. The moment you want to go and do interacting theories, this immediately becomes harder, and you have to do it somehow in perturbation theory, this calculation, but you can do it. So then, what we did with Vladimir in this paper is we said, okay, first of all, this is let's postulate this as a theorem now. So what are we doing? We are computing some W block and point block with insertions of currents that we don't know what they are now, divided by the block without the insertion of the current. And then this object that is denoted with this double bracket, when we send the epsilon1 and epsilon2 to 0, because the curve doesn't know about them, it should give the coefficients. So let's take now this as a theorem, and let's try to see what happens. So that's precisely what we did, and that's what we got. So first, because you get all of these equations, you know what is your symmetry algebra. And the symmetry algebra came out to be WKN. By the way, at the beginning, I really thought that it should be some very exotic, crazy algebra. But the more I was matching coefficients, the more it was hopeless. It was not an exotic algebra. It had to be this stupid. So it's just W algebra, just that the n multiplies k.
But you said that the pole now you have a simple pole.
Yes. So no, good. The simple pole, very good. So the simple pole was for the minimal punctures, but the maximal pole is
Scale.
this.
Okay. That's why the scale.
Yes. So the maximum phi L thing that you can get is n. So that's precisely why you have Wn. Of course, you have to do everything to see this, because you really have to match, all the coefficients which lead to all of the representations, null vectors. So everything is encoded in the curve.
And but do you have kn worth of phi? I thought you just have.
Good. So some of them are zero because of the orbifold condition.
Oh, so the WKN algebra with an orbifold.
Yes. So here is the answer. It's coming.
Okay.
So first of all, first you say what should be the algebra.
Okay.
So you say, okay, that's my algebra. Then you have to ask the question about representations. So the answer is the representations that you get are completely standard representations of the WKN algebra. Completely standard, and especially when you look at the full puncture and the minimal puncture, they are specific type of choices of the parameters. And in fact, this is precisely what it is. So you need to make your SUKN n equal to 2 theory to obey this orbifold condition for both m's and a's, and you match precisely the 2D CFT blocks.
Is this is probably a new algebra then, right?
It's not a new algebra. It is just the old algebra, but with this. Why it would be? When would you have a new algebra? You would have a new algebra if you could argue that, for example, some generator should be missing. And I did this at some point. There are, for example, generalizations of W algebras that they don't have all, J1, J2, J3.
Yeah.
They have only, let's say, half of them.
But I thought you do have things missing.
No. But these things that are missing, it's not because currents are missing. It's not because generators are missing. For this, you have to do the calculation. So I tried that. I clearly tried that. But this is not because of the choice of the algebra. It's because of this choice. So if you try to take these algebras where generators are missing and try to match the curves, you cannot. You get some mismatch.
Sorry,
Yes.
in the first definition there,
Yes.
so there you have phi's on the right hand side, and j's on the left hand side.
Yes.
Your algebra operators and the Coulomb branch, there is a match, right? And you are saying that the WKN would have all the generators.
Yes. Very good.
So phi should also be all of them.
But some correlation function can be zero, not because this object does not exist to insert it, but because the specific momenta that you put in makes it so that it comes out to be zero. That's what I'm saying.
But phi's, we know that not all. There are not so many phi's.
Yeah. They are only specific ones.
N phi's.
Which, so let's really, if you take the curve, or you shouldn't take the curve, you should take these precise blocks of this n equal to 2 theories with SU and K, and you make this identification, you will make these things vanish. And my claim is that if you take these other W algebras where generators are missing and you try to do the computation, you will never match the phi's. That's my claim. This is something that I don't know, apart from a crazy calculation, I don't know of any other way to do it. Now, we are almost there, because, this is really almost like it's n equal to 2, right? It's almost stupid. In fact, when I got it, I was disappointed. I really wanted a crazy algebra. But no, there is no crazy algebra. So we have, after doing this homework, the symmetry algebra and the representations, but we have them when the epsilons are switched off. Now I want to turn them on if I want to write some instant on partition function down. Now, first of all, the first thing that I demand, and this you can say it's an assumption and you don't like it, but in all of the examples that we know in our life, this is precisely what you do. You write down your multiplet, and you demand that when you turn the epsilons on, maybe the precise, descendants in the precise points where they are can become linear combinations of the previous ones. So the precise form can change. But what is not allowed to change is the null states. So you should have the same null states in the same spots. So that's assumption number one. Then there is assumption number two. And by the way, the moment you make this assumption, you can immediately write something down. You just write it. Now, you need to tell me when you write this object down, precisely what is the map between these W's and the masses and the A's and all of this stuff that you write. So, and in order to do that, you need to know how to turn on the epsilons. So the assumption there is that I turn on in the W's and in the central charge, because the central charge is also in here, the Q precisely the same way as in the naive Liouville and Toda. So for example, when I write C, let's say so it will be anyway rank plus this Q squared. So that's how I turn on my epsilons. And the same thing, this is the Weyl vector. This is rho. So you have to, you sum over all the positive roots and then you define an inner product, and this will give a coefficient here. For example, for Liouville, this is 1 and this is 6. And then when you do crazy Toda, you have higher powers of n there. And the same thing, delta has to be something of this form. So this is how I turn on the epsilons. And that's it and nothing else. So if you do this, W is the higher current. So for example, you can have a W3 if you have... So not certain charge, this is the eigenvalue of the higher spin generators. So it will have a form like this. Let's say that there is one way to write your, this is a 3 vector with a condition. So maybe you can write something like this. Q, and maybe the 3 of them, the sum of them is 0, something like this. So, but that's how I turn on my Qs. And then there is Q4, and go, So the moment you do this identification, you write something down and you look what you wrote down, and it's precisely the Nekrasov partition function with this orbifold condition. So good or bad, I don't know, it's very easy, but that's what you get.
But
Yes.
If you take n equals to 2, so that's even if I don't worry about
Yes.
n equals 1 at all, right? I just take n equals to 2 as UK and theory. Okay, I do the same business that we've done in the earlier thing. You write down these blocks, these are the curves and so on.
Yes.
Pure n equals to 2.
Yes.
From there you guess the block and so on, and you are the instant on partition functions
Yes.
as you can,
Yes.
right? Helps you match.
Yes.
That is no question. Now once you match, this procedure would just follow through, right?
Yes, I want
So
to
in
say
that
yes.
sense, that was expected, no? That the fact that because you are doing this business to the same object. You match things at the level of n equals to 2, and you do this business the same object.
So there is one thing that is not expected, why it should not 100% be. I mean, a posteriori, I also want to say that, but a priori, there is something that is very different. And these are the coordinates, when you write in terms of these objects, you should be careful. Of course, as we know very well from n equal to 2 theories, the map between U and the A's is a very terrible, this mirror map, it's a terrible function. But by the way, now that we are actually in this slide, let me say one thing. What I am doing here is I am at the orbifold point. So what does it mean? It means that, because here I imposed the orbifold the way I did, but I didn't do anything to the NS5 branes. So what this means is that I'm looking at a sub-case in which the coupling constant of all of these objects are the same. So this partition function that I got is correct only at the orbifold point.
Okay. So that's what breaks the symmetry. Okay. But are the individual coupling constant exactly marginal?
Yes, they are exactly marginal.
So all of them are exactly marginal?
Yes.
Why is that?
I mean, you have to do it. I mean, this is the same. Okay, the old school people, like when they were doing the ADS orbifolds, they were calculating one loop beta function and so on. But then you can realize that this should be an all-order result. Okay, let's continue. So now I want to rederive. So this, by the way, this calculation that I will do now, I want to say that it's away from the orbifold point. But when it goes at the orbifold point, I get the same answer, basically. So this is the point. So let's go. Let's go for it. Okay, first of all, to do this, you have to remember your string theory class, right? So you take K. So first of all, N dp branes, these are the big ones, and K dp minus 1. And you say, let's write down the action on this N dp branes. And when you do that, you remember that there is this term. So there is the F wedge F, which we know is the instanton factor. And it is coupled to this P minus 3, Ramon. And so these, they can only be if you turn on this type of branes. So you identify the P minus 4 branes with the instantons on the dp. So that's the first step you need to do. The second step you need to do is you remember that when you want to construct your instantons, okay, one instanton everybody can do, but when you want to do more instantons, you have to solve this very funny auxiliary it's just a mathematical prescription that I think most of the physicists, they almost don't know why these crazy mathematicians ever did it, the ADHM construction. But then you can embed, if you look at this string theory setup, you can in fact understand precisely this ADHM construction, and you can realize that this I and J, K by N matrices, they come from dp minus 4 strings. And then these B1 and B2 matrices, they actually come from strings between the dp minus 4 branes. So you can derive this, and these are precisely the F and the D term equations on the gauge theory that lives on here. And in fact, it's even better. You should really say that the instanton moduli space is equal to the Higgs branch for the gauge theory that lives on here. So this is, and this doesn't care about, how much supersymmetry you have. This is just a correct equation. Good. You have to have supersymmetry in order to have the interpretation as F term and D term.
The right hand side is supersymmetric, the left hand side is not.
But by the way, these equations, the ADHM construction is the correct construction even for non-super. So pure Yang-Mills, this is the ADHM construction. So it has to come from some construction like this where you break supersymmetry. Even this should be the case. But nonetheless, for supersymmetric theories that you have some type of notion of a Higgs branch, the instanton moduli space should be equal to that.
That's what I mean. So on the left hand side, it's totally non-supersymmetric notion.
Yes.
Just instead of moduli space.
But
On
here,
the right-hand side, it's a superset.
yes. Very good. Now, okay, there is clearly no Nekrasov for n equal to 1 theories, but let's review what Nekrasov was doing. So one of the ways you can write Nekrasov's calculation is that he was calculating, so he was doing a trace over the instanton moduli space of some index with these fugacities, where he had to choose psi as some linear combination of epsilon1 and epsilon2 because he was borrowing the results from the topological twist of Witten. So, but this is what he was doing for xi that is a linear combination of the epsilons. Now, if you pause for a moment, you can start seeing that you know this thing, basically. You really know this. First of all, from this equality, we know that we need to put this here. So now we want to study a lower dimensional theory with some type of index. And then if you pick, let's first, so just because I like it, let's pick p equal to 5. So this will be some 6-dimensional gauge theory for which I want to compute the instantons. Let me put it on a T2. So the D1s will be wrapping the T2. And this is really now becoming, so this instanton index is becoming a 2D superconformal index of the gauge theory that lives on these D1 brains. And to do things nicely, you should also go very slowly and identify all of these things with the 10-dimensional generators that you have, and you can do this. And the moment I do this, and I have made this parameter identification, I can just go and copy all your papers. Very good. So, first homework. So let's remove all the orbifolds. We don't know anything. Let's try to see if what we are saying makes sense. By the way, to be honest, for me also this case that is known is very cool. Because before, if you would tell me derive Nekrasov by yourself without looking at any book, I couldn't do it. But now I can do it in less than half an hour. So this is, I think, amazing. Yes. So first, let's just take the D5D1 brain system. So the gauge theory that lives on this is this. So here I am using some 4,4 notation. So this is a 4,4 vector multiplet and so on. So I write this thing down. The moment I have it, I make a table with all of my charges of all of my fields, and I compute the index. And of course, up to parameter identification, because when you write an index, you use some fugacities, you don't really know what they are. Up to this parameter identification, you can match it with the instanton partition function of the 6 D theory T,2 on R4 cross T2. So you can match it. This was calculated, for example, by Vafa, by using topological strings. Anyway, there are many ways to do this calculation, and this is known. It's also called M strings, and you get on the nose the same thing with the index. And this is very good because now also you start matching your parameters and you know precisely what you are doing. And the moment you write this object down, you also have parameterized your torus with 2 radii. You take one radius to go to 0, and you get the instanton partition function that we know very well for the 5D maximal super Yang-Mills with a mass parameter, a mass deformation. So you get this on the nose, and you go further one more down, and you get n equal to 2 star. And all of these steps, I mean, you have to write the things, but they are very easy. Here you get some theta functions. The theta functions easily go down to sines, and this goes down to rational. So it's really stupid and easy to do this. So now I need to start doing my orbifolds. And yeah, okay, this was my favorite thing 2 years ago. I thought that life is just orbifolding an index, and also that's how we did the n equal to 3 stuff. I thought that that's all that there is in life. So what, maybe I can write the recipe. It's extremely stupid, So the index is just a bunch of characters. I don't care what it is. It is, oh. I think I destroyed this. Do you want to try to fix it? And take another one. So the index, let's write even the single letter index. This is a bunch of characters with stuff in it of the superconformal algebra. Maybe it's broken actually, or you fixed it. Okay, amazing. So I'm writing now schematically the single letter index. So it's some type of character from the superconformal algebra times some other character from the gauge group. Right? Very nice. So this is the original index. And it's really a bunch of characters from two different groups. So in order to orbifold this type of thing, what you do is you define a more refined index. So let's also maybe recall that the index is some minus f. And here I have, I don't know, different fugacities with different, type of generators from these groups, where the important thing is that all of these things commute with the supercharge that you chose. Great. So now I have the idea, it's very easy. Let's refine my index by an extra, because I like it, where here I put precisely the rotation of the orbifold. Again, to be able to do this, I need to pick my Q such that it commutes with the orbifold, but this we did in the very beginning slide. So you write these equations of the Q with all the gamma matrices, Q, and of the orbifold, then you find which Q stays. So first you identify which Q commutes with the orbifold, and this is the one that you use to compute your index. So the moment you have this, you generalize this thing, and you also have an extra fugacity in here. And you can write this down. Of course, this is not correct anymore. You need to now project out all the states that are not invariant under the orbifold. So if you have 1, or if you have e to the k, or multiples of that, this you keep. This is equal to 1. But if you have e to the k minus 1, you have to drop it. So that's what you do to this index. And then you get the correct, and this is precisely at the level of the index, how do you impose this Douglas and Moore, so our favorite equation from the previous time. So this is precisely at the level of the index. And I don't care what these things are. This is just some j that is part of my algebra, and I just do this formal procedure. I close my eyes and I do it. So now, yes. I think it's more clear you die. It's, yes. It's, I follow all the rules that I am supposed to follow. Good. So, okay, good. So first I practice. So first I want to do n equal to 2 theories that we know the answer. So first we do one of the two orbifolds. So here I have only the, whatever was it, 7, 8, 9, 5, 7, 8, 9 orbifold. I do it, and I precisely get, first of all, in the 6th dimension, it already has a meaning, this object. I look at it and I find that it's precisely this M strings or an transverse orbifold that Baffa had in the paper that he wrote after the M strings paper. Then, we do Kaluza-Klein to go to 5D, and we get this nice SUN to the M quiver. And in 4D, I mean, again, this type of quiver, but not with signs, you get the rational answer. So this is the answer we know from Nekrasov, and we are very happy. So now we just turn on the other orbifold, and we just do the procedure. We close our eyes and we do it, and we get something. And by the way, we get at the beginning some elliptic type of object, some trigonometric type of object after the reduction, and then some rational type of object. And the rational object is the one that should be the Nekrasov partition function. Okay, first of all, Good. If you put this orbifold condition, you actually get the same answer that we got before, so that's very good. So this means we are not completely insane. Just one thing, so here I wrote how things go down, so this is 6D, 5D, 4D. Here, when you do the second orbifold, because you have this torus, and this orbifold, you see here is the torus. Sorry, here. This is where the D1 is. The orbifold acts also here. So you have to be careful. So what you really have actually, here is a 1,0 with a defect on it. By the way, this thing is precisely the same defect that Tachikawa and Kano studied. So if you remove this orbifold, this is precisely the setup of Tachikawa and Kano. And then you can go down to 5. Again, you will have a 5-dimensional theory with a defect. And only in the 0 thing there is nothing, and you just have a pure n equal to 1 4-dimensional gates theory. So basically that's it. That's what I can do. And when you impose that you are at the orbifold point, you match what you got before. And I have to say that I suspect, but...
So this defect is just M2 branes, a bunch of M2 branes?
Sorry?
This defect is a bunch of M2 branes?
The way I can understand this defect is that you have an orbifold, so here you can actually understand it. So you should think that here, if I uplift this to M theory, this is where the M5 branes live, and this defect is actually touching the M5 branes into 2 places. So it's a codimension 4 gadget. And I can only describe it as an orbifold, but again, this is also precisely how Kano Tachikawa did. So that's very good. Okay, now here, this I like. I mean, this doesn't really add any information, but it makes you understand how it looks like. So here I have for you, I mean, I can clearly engage nodes and play the same game in the Hanani-Witten setup. So this is the SU2 for flavor, how it looks. And this is a partition function. And I have here underlined with the specific color from which strings which thing comes. And you can do the same thing if you do the orbifold. And precisely you can follow from precisely which type of strings, because in the end of the day, this is just an open string spectrum that we put together with these characters. So that's what we are doing. So there is a very clear understanding who comes from where. So this is, I think, very important. And to be honest, my dream would be to somehow try to make this a theorem. Yeah. Good. Okay, so what we have done, let's summarize. So first, we have constructed the curves at the orbifold point. Then from the curves, we guessed what should be the algebra and the representation. And again, if you try to put that, because I really didn't want at the beginning to have this stupid simple algebra, I wanted to have a crazy thing. So I tried all the crazy things that, have these generators, and they are all wrong. So they don't work. So the moment you have this, you write down blocks. Nobody can stop you from doing that. And this gives you a guess for the instantons. Then from this system, you can have another calculation for this instanton partition function. And at the orbifold point, it matches. Now, okay, by the way, the first thing is something that, I want to do for a long time, but this is a little bit laziness, a little bit whatever. So one should be able to just do honest instanton calculations the way Dore and friends tell you, and you should be able to check the first couple of instantons to see what's going on. And this way also you can understand precisely what is the meaning of this epsilon1 and epsilon2. Now, another thing that hopefully, it should have come out basically, to be honest, a very long time ago, but okay. So you can go away from the orbifold point. So with my student, we re-derived the curves away from the orbifold point. So I have the full thing. And you can start to ask all the questions from the beginning.
So away from the orbifold point.
So all the coupling constants, no.
Coupling constants are
Yes,
different.
all the coupling constants are different. So we
Okay,
stay in the Coulomb branch, but all the coupling constants are different.
But in the curve that you showed,
Yes.
was essentially the curve of the SUNK with some modding out.
Good. So now what happens is that the different mass parameters, they become functions of the relative Q. So good. So, okay, maybe I tell the answer very
I
quickly.
see, but still there is some modding out action.
There is, but they become also functions of the relative Q. So there is a very nice renormalization game that you can play. And you can really write down the answer explicitly. It's very nice. And one of the reasons why I like this is, so if you write, so this is the stupidest Z2, Z2 quiver, right? If you send this to go to 0, you get super QCD, so which is super cool. So, and for now, I have to say that I have not studied the curves carefully enough. I don't see why taking this limit is bad. I really don't see. I mean, there has to be something, but I haven't seen it.
But why do you expect it to be better?
I mean, this is a very special, this is, this is real physics. Can I reach real physics with what I'm doing? This is why I expect it to be. I mean, I don't know, maybe it's not. Maybe not. Yes, so okay, then this is the other can we do other theories? For sure, all these classes gamma we can do, but then maybe other things that are important, for example, for ADS-CFT, maybe the beta deformed, this type of things, they have some good chance to go through. And now, okay, good. So this is something that in fact I have spent infinite amount of time on, and it's a very, very, very difficult problem. Because, if you know the 3-point function of the CFT, you are done. You can write down the partition function on S4. In fact, I also spent a year trying to do the localization, and I can tell you completely privately what happened. It still might be possible to work, but I died, and all the students also that they were involved died. But the way I was phrasing also the problem, in order to get it from the CFT, this is another very difficult problem. I was writing down the crossing equation and I was trying to solve it.
But didn't you say that this has a solution DOZZ? And then you again orbifold again?
So when you go to, first of all, to higher W algebras, so DOZZ is only for the SU2 case.
Okay, but there is corresponding.
There is a corresponding thing, but good. Good. So this perturbative part, you can also calculate it, at least half of it, by yourself, by doing the determinants. Because when you have a free theory, you can always do the determinants. So I've done this calculation, and I got something. And then I did the naive solution of it's Fatev with some other people. And they basically don't match, but they don't match up to one thing. The one is the kth root of the other.
No.
Which is insane, and I have a lot of speculation why it's like this. So it's a crazy complicated function, whatever it is, with all these epsilon functions. But when I just do the determinant, I get kth root of what I would have gotten if I would have solved the bootstrap.
Well, that is very close.
It's very close, but it's not the answer. So if you can tell me what to do this square, this is maybe.
So you want the determinant you want the kth power of this answer, right? To be right?
Okay, and anyway, to finish, one should also try to do this, to put the orbifold in this construction and try to do. Yes, I think that's it. Yes.